So welcome back to our little computer logic series that I'm calling the OMNI series, which OMNI is Latin for all, because we're going to cover everything computer related in this series. And this episode is all about how do computers add numbers, which seems like a very basic thing that a computer should be able to do after all. Because if you remember from our first episode, computers can do three functions. They can fetch, decode, and execute. They actually do this quite well. They can do this billions of times a second, but we're covering with the basics first before we go this far advanced. But how do computers fundamentally add numbers? So let's go all the way back to kindergarten so we can understand how humans add numbers, and then we can translate this into a binary computer addition sequence. So if you remember, how we add numbers, we add the ones first, the tens first, and then if we add two numbers and it goes over 10, we have to carry the one. Very basic. So let's add these two numbers together, 17 plus 38. So 7 plus 8 is 5, or 15. So we're going to put the 5 at the bottom, and then we have to carry the 1, because the 1 cannot be in the ones place, it has to go in the tens place. So now if we look in the tens place, 1 plus 1 plus 3 is 5, so we get 55. So a lot actually just happened there. We took these two numbers, we added them together, and then we have to make sure we carry the 1 properly into the next digit, and then add three numbers together. So now we got to do the same thing with binary numbers. So we have these two binary numbers, 6 plus 7. We're going to add them together. We're going to get 0 plus 1 is 1. And then we go to the next column, which is 1 plus 1. So there's a problem right here, actually. And that's because binary can only show two states, which is 0 and 1. So if we add two numbers together and it goes over 1, aka if it's 2 or higher, we have to carry a 1. So 1 plus 1 gives us 2, which we cannot represent in binary. So we have to carry this 1 over. So 1 plus 1 is carried 1, 0. And then we're going to get 1 plus 1 plus 1, which again, that's 3. So we can't represent that in binary. So we have to carry a 1, and then we have to bring down a 1. And so then finally, 1 plus 0 is 1. So we get the number 13, which is correct, which that's exactly what 6 plus 7 is. It's 13. And so how can we translate this essentially into transistors, or how can we translate this into logic gates? Since computers are fundamentally made with logic gates, that's what we need to create in order to get an addition circuit. So let's look at one column of numbers and really kind of analyze how do they work. So 0 plus 0 gives us 0. Wow, this is shocking. So if we have 1 plus 0, we get 1. Makes sense. But if we flip the two numbers around, 0 plus 1 is still 1, commutative property of addition. But notice 1 plus 1 gives us 0 carry 1. Okay. So if we look at the sum, it kind of looks like an XOR gate, logic gate. We have, if both of the added numbers are 0, we get 0. If both of the added numbers are 1, we get 0. But if only one is 1 and the other is 0, we get 1. That's literally an XOR gate. And if both of the numbers are 1, we have to add a carry to the next column, which is an AND gate. If both of them are 1 and, then we output a high. So we can make an adder circuit with XOR gates and AND gates, which is actually pretty easy to make because these are basic building block gates and it's nothing complicated happening. So now we're going to go into a little computer simulation so we can actually build this gate and then build our computer in real time in simulation. And I would like y'all to join me, and you can get the software for this computer simulation in the description below. It's by Sebastian Leahy. Did a phenomenal job making this. You can run on most computers with basic gates, but as we get more complex, you might need a beefier CPU in order to handle all the complex logic that we're simulating in real time. But again, it's in the link in the description, and let's go into the simulation, and I'm going to explain how it works and how we can use the simulation to make CPUs. So now we are in our simulation, and we're going to continue to make our adder like we talked about in the previous part in here. So first things first, we're going to create a new project. I'm going to call it OMNI because that's the name of the series. Excuse me, OMNI. So when you notice when you enter the simulation, we only have one logic gate, which doesn't make any sense. We have these ins and outputs in our menu. So first things first, we're going to go to our preferences in our menu. We're going to put this to tab the toggle, yes, and then we're going to put straight wires to always. So this will just help our simulation look a little bit nicer, and will keep us organized because we can see what our pins are named. So all the other logic gates can be made with the NAND logic gate, if you didn't know that. And let's go through a little bit of basics of how the simulation works. So if you click inputs, you see all the inputs and outputs you have. We have bytes, nibbles, just singular bits, and these buttons and switches. So if you hold shift and press it, you can essentially add as many as you want at one time. And then we take it out like this too. We can click our NAND gate like this, and we can make a little circuit to demonstrate how this works. So this is our AND gate. So both of them are on, the output is on. And we need to make all the other logic gates because we don't have them yet. So that's what we're going to do right now too. So this is our AND gate. And then if we can manipulate, we can continuously manipulate this one gate right here, kind of funny enough, to get all the other gates. So this is going to be our NOR gate. And make sure you click save as and not rename so you don't accidentally duplicate or kind of go over your other gate. This is our OR gate too. So you see, it works like an OR. Excuse me. And so all we got to do is delete delete this wire right here and this one right here, put a little AND gate, NAND gate, and now we have our XOR gate. And then this is our XNOR gate, just like this. And we delete all of this and just have one. We need to make a NOT gate. And we're gonna, if we press customize, we can customize the gate to different colors and just different styles. So we're gonna make our NOT gate as small as possible. Now if we go into our library settings, we can see all the different stuff that the simulation comes with. We have merges, so we can convert 8 bits to 1 bit and so on. We have our ins and outs, memory, display, and other stuff too that we can really look at. But this one, we're just going to go into how computers add. So if you remember from our Blender simulation, we kind of discovered that all you need is wait, excuse me. Yeah, that's fine. All you need is an XOR gate and an AND gate, and you can make two numbers be added to each other. So that's exactly what we're going to do right here. So we hook these up just to each of them, and then we hook the outputs up. This is going to be our carry, and this is going to be our sum. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and then 1 plus 1 is 0 with our carry light on, which is exactly what we got in our Blender simulation. So we can save this chip as our half adder. And we're just going to rename this half adder and make it as small as possible just for convenience. And so we're going to customize it. We're going to give it a different color too, like this dark blue, save as. Then we're going to click new chip. And we take two half adders, an OR gate, we can make a full adder. And a full adder can add 3 numbers together and give us a binary 2 output. which is very useful because if you remember in our Blender simulation, we sometimes do need to add three numbers together because we have to add that carry from the previous calculation onto our new number. And so we need a full adder in order to do this. And so that's what this circuit right here does. And we're going to demonstrate it after I rename all of these pins for our convenience. So we have 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and then 1 plus 1 is 0, 1. Now if we have this carry on too, it kind of acts like another input. And so we can essentially get the same outputs as this, which allows us again to add our carries to our previous calculation. So we can save this as our full adder. We're going to customize it, just make sure it's as small as possible. We're going to save it, new chip, and now we're going to make an 8-bit full adder. So we need 8 of these. So we're going to hold shift and click it 8 times. 1, 2, 3, 4, 5. There we go. Now we're going to go into our library, get a merge, and I'll show you why we need this in a second. So 8 to 1 bit, use it, hold shift, we want 2 of these. Then we want to go in our library, and we're going to get a 1 to 8. And now we're going to go to our inputs, and we're going to click an N8, hold shift, so we get 2 of them. And then we're going to get an output of 1, just like this. So we connect these. We have a more convenient way to kind of add these numbers instead of clicking 8 of these little circle things. The simulation already provides us with a nice 8-bit LED matrix already. So we also need 1 input and then 1 output. And this is our carry in. So carry in. And this is our carry out. Let's carry out. So we're going to hook this one up just like this. Hook this one up just like this. Since the first 2 numbers that we add never have a carry, and then we're only adding 8 bits together, so we don't need a 9-bit carry. And that's essentially why we have these 2 buttons just like this. So we're going to hook our inputs up. The top one is going to be input A. I'll rename it real quick. A and B. And we're going to hook these up just like this to our inputs. And now we're going to hook up our outputs to this right here, just like this. And so this is where the really magical part happens. So the carry out from the first adder is going to go all the way up to the input of the adder right above it. And we're going to do that for each of these. And that allows the previous adder to know, hey, this number went over 2, so we need to add a carry to the next operation. And it does this instantly. So there we go. Now we're going to click our output, put decimal unsigned on, and the same for inputs. So we can kind of see what these numbers are that we're adding, because we can't really convert binary to decimal just yet in our heads because we're not pro computer scientists. But now let's add 6 plus 7, our previous calculation, and we get 13. So you can see, if we look at it, this number's on, this one's off, so we get the sum out. We have no carry. So 1 plus 1 gives us a sum of 0 and a carry. So we add the carry to our input. And then 1 plus 1 plus 1 is 3. So we get this output in this carry on, and which lights up the next one. So it works as it should, and we can add any number we want to, and it will give us the exact answer instantaneously. For example, 100 plus 68, 168. But I want you to look at something. So if we add a number that's really large, like 192 plus 100, that should be 292. But 8 bits of binary data can only hold numbers up to 255. So the number cannot be represented with a simple 8-bit data set. So our carry out goes high, pretty much telling our computer in the future, hey, the number we calculated is actually way too high to be represented with the bits that we have. We should do something about this, and then we can. And that's how computers, an 8-bit computer, can calculate numbers that are much larger than 8 bits thanks to this carry out. And then our carry in will allow us to essentially add whatever the number is by 1. Because we're carrying in an input, in which these two are closely related, which again will allow us to add numbers that are more than 8 bits on an 8-bit computer, in which that's exactly how an Arduino works. So an Arduino is an 8-bit computer, but it can add numbers that are greater than 8 bits thanks to this little carry out sequence in computers. And that's how early computers also worked too. But this is essentially our full 8-bit adder. So we're going to save this as our 8-bit adder. And if we click new chip, we can see it, and it looks exactly how we want it to. And it saves a lot of space too with these 8-bit inputs. So that's it for this episode of the OMNI series. We just want to make these adder so we can understand how computers can add numbers together. And I hope this really helped your understanding of it. As always, links in the description if you're interested in any of my products. We also have a free Discord community where you can join, where we have members actively on it right now. And then next week, we're going to go over some more calculations. We're probably going to go over subtraction. So come back next week where we'll talk about how do computers subtract numbers, which is a very fascinating and counterintuitive way. But thank you for watching. So before we end this episode, I do want to show that you can actually make a full adder circuit in real life with these with these LS chips that we've talked about in our previous episode. So this is an LS BJT transistor chipset, and we can make it. So 1 plus 0 is 1. 1 plus 1 gives us 2. And then all 3 of them on give us 3. And they work in any order that we want it to work. So this is actually how a real-life computer would work with real transistors, not just in a simulation. So the simulation is very accurate with how we need to wire up these logic gates in order to get the outputs that we want.